In today's lesson, we are going to be looking at functions and function notation. So just a little bit of a review. Right, we want to state the domain and range of the relation shown in the following graph. So here we have what's called the Batman equation. There is an actual equation. It is quite long and tedious, but if you enter it into Desmos, it does give you the Batman symbol. But we want to state the domain and the range for this. So again, remember, domain refers to the x values. So where do our x values go? X is again horizontal. We can see that it doesn't go anywhere beyond here or below here. So regardless of the max and min or the highest and the lowest, it does at least start off the same. X is any real number such that. Now our restrictions. Do we have any restrictions in this case? Well, we do have restrictions. It does not go on forever. X is actually greater than -7. So -7 is our minimum, but it is less than +7, which is our maximum. So that means the domain for this function is x is any real number, given that it is greater than or equal to -7, but less than or equal to 7. For the range is again set up the exact same way. Squiggly line or squiggly bracket. Y is an element of any real number such that, and then what is our highest and our lowest? Right? Say it looks like approximately here. And the highest it appears would be here. So the lowest, right, we can make an approximation, maybe about -2.5, or say -2, maybe a bit more than half, we'll say -2.7, just for it's a little bit over half. So -2.7 is the minimum, so y is greater than or equal to -2.7, but it is less than or equal to the highest value, which is 3. So that is the domain and range for this function. Now the next question is this a function? In this case, because we have a visual or a graph, we can go through and do our vertical line test. Realistically, in this case, I only have to do one, right? I'm going to draw my vertical line. You can see that it touches twice, so that means it is not a function. So no, it is not a function. A little bit of review of yesterday. What determines if a relation is a function or not? Right? Different answers, right? It should all be kind of coming around the same general idea that for every x value, there is only one y value. Right? If there's 2 y values, it is not a function. Right? 2 y values is not a function. We only want one y value for every x value. How does the vertical line test help us determine if a relation is a function? Well, we just had an example of how we used it, right? So the vertical line test basically states, or it will test, only crosses at one point, right? If it's for testing for a function, which is what it does, right? So it should only cross at one point if it's a function. What is domain? Again, we talked about domain. Domain, quite simply, is the set of values x can take. So what are all the possible coordinates of x or values of x? And then the range is the set of values that y can take. So again, domain is x, range is y. Now, the new thing that we're going to be looking at is finding values using function notation. So we've talked about what is a function. Right now we're going to be looking at function notation. So what does a function do? Well, we kind of talked about it a bit with the definition being that there's a y value for every x value. But in general, what a function does is it takes an x value, performs some sort of operation on it, and then gives an output or a y value. And essentially, basically, like it's like a calculation, like an equation. We've seen examples of this before. We may not know it as a function, but we've seen examples like y equals mx plus b, y equals, right, the ax squared plus bx plus c, right, our quadratics. Those are functions. I can plug in an x value and it will give me a y value, right? That is essentially what a function is. Now, what does function notation look like? Right, so function notation usually looks like this f bracket x equals. Right? So that is generally what function notation looks like. Right, this kind of setup here, a value, and then in brackets or a variable, and then in brackets another variable. So this whole thing here, this generally replaces your y or your dependent variable, right? So it usually replaces the y value. So if I look at the above examples, instead of y, I would have this representation. So it'd be this and then equals mx plus b, or this and then equals ax squared plus bx plus c. So this whole something to do with x is basically like some sort of calculation, some sort of expression that has the x variable in it. Now, I keep saying this symbol, but we actually have a way to say this, right? So this whole thing is actually read as, and we read it as, we either say f at x, so the f value at this specific x value is equal to whatever, or we might read it as f of x. So the f of this x value is blank, right? The h, or the height of this value, or the function at this x value, is equal to, the function at this x value is equal to. That's essentially what it's saying, right? So it's just basically a fancy way to word things. It does make things a little bit shorter. It saves us from having to write things out to be very descriptive, and it allows us to have more detail in some of the calculations, right? So just a general thing, we input an x value into our function and it spits us out an answer, right? So the function at that value, or the function of that value. So for each of the following functions, determine f at 2, f at -5, and f at 1/2. So essentially all this is saying is I have this function here. F at x is equal to 2x minus 4. Or the function at x is equal to 2 times x minus 4. So what this function notation is telling us, it's basically telling us to plug in these specific values for x and solve. So for the first one, f at 2 is equal to 2 times 2 minus 4. So all we're doing is substituting the value in for x. We get 4 minus 4, or 0. Right, so that means that f at 2 equals 0. Now, a common thing is we do not do anything with this f at 2. We're not trying to get f by itself. We're not trying to solve for f, right? F at 2 is basically just a term, right, so to speak, or it's one singular thing, right? It's one variable. It's telling us the function at 2 is equal to 0, right? So now that tells us that we have the point 2, 0. So we have our x value and then our y value, our coordinates, right, from this. The next one f at negative 5, do the same thing. Replace the x value with the value that we're looking for. So the function at negative 5, or f at negative 5, is equal to 2 times negative 5 minus 4. Negative 10 minus 4, we get negative 14. So this gives us the point of negative 5, negative 14. So it gives us a value or a coordinate in this function at a specific x value. And the last one, same idea. F at a half is equal to 2 times 1/2 minus 4. So we have 1 minus 4, or negative 3. So basically we have a point 1/2 negative 3 for this function. So for B, same idea, going to go through and do the same thing. We have the different values of x. So first one we have f at 2 is equal to 3 times 2 squared minus 2 plus 7. 2 squared is 4. 3 times 4 is 12 minus 2 plus 7. We get 17. So therefore we have a point 217. F at negative 5 for the next one is 3 times negative 5 squared minus 2 plus 7. 3 times 25 is 75. Minus 2 plus 7. So we get 80. So negative 580 is one of the points. And f at 1/2 equals 3 times 1/2 squared minus 2 plus 7. Oops. This one I will need to use a calculator for. 3 times 1/4 is 3/4. Minus 2. Oh no, shoot, I've been making mistakes. It's not minus 2 for these ones. It's minus, my mistake, minus 5 plus 7 minus, so it becomes plus 5 minus 7, or sorry, plus 5 plus 7, 87. Forgot there's the x value, so I need to plug that in. So minus 1/2. So 3 times 0.5, or 1/2 squared, minus 1/2 plus 7. We get 7.25. So we have the point 1/2 and 7.25. So again, all it's telling us to really do is plug in a value for x and solve. For C, f at x is equal to 87. This means regardless of what the x value is, so for example, f at 2 will equal 87. F at negative 5 will equal 87. And f at 1/2 will equal 87. So this is just a fancy way of saying this is basically a horizontal line, because regardless of what the x value is, the function gives us the same y value of 87. So try to go through the last one on your own, right? Plug in the go through the different values, f at 2, f at negative 5, f at 1/2, and see if you're able to basically plug in and calculate using this new function, f at x is equal to 2x divided by x squared minus 3. So pause the video, try this on your own, and we'll come back with the answers. So coming back, we should have these 3 points. When f at 2 is equal to 4, f at negative 5 is equal to 5 over 14, and f at a half is equal to negative 4 over 11. So again, we're just plugging values in and determining what the function is equal to given those x values. The next thing we're going to look at is mapping diagrams. Right? And mapping diagrams is a representation that can be used when the relation is given as a set of ordered pairs. So in a mapping diagram, the independent values in one oval are joined to the dependent values in the other oval using arrows. A relation is a function if there's exactly one arrow leading from each value in the domain or independent. This indicates that each element in the domain corresponds exactly to one element in the range. Right? So exactly as we kind of have listed it before, or mentioned it before in terms of the domain and range. Right? So domain and range, independent, dependent, same idea, x and y. You could also say same general idea. Right? So one arrow going from the independent to the dependent or from the domain to the range. So for each mapping diagram, we want to write the set of ordered pairs and state if it's a function or not. So if I look, right, my ordered pairs, so I have 1 and negative 5. Because for the value of 1, it goes to negative 5. I have 2 and negative 1. I have 3 and negative 5. I have 4 and 0. 5 and 0. 6 and 5. 7 and 8. Now, again, we talked about this before previously. As long as there's only one y value for every x value, we are okay. It can be the same y value or the same range as another value, but as long as there's only one y value for that x value. In this case, there is, so this is a function. For B, you can probably tell by looking at it that it's not going to be a function because we have multiple y values or multiple ranges for a given domain or given x value. So we know it's not a function. Let's go through and write out the ordered points anyways. So we have 2 and 1 or 2 and 2. We have 5 and 3. We have 8 and 7. We have 11 and 5. 14 and 4. And 14 and 6. So we see 2 instances where we have multiple x values for a given y, or multiple y values for a given x value. So again, based off this mapping notation, based off the points that we're getting, it is not a function. Lastly, look at some applications of function notation. So rather than given an equation, given as y equals something with x in it, we can use function notation, right? So this is saying h at t, or if it's an application, we may say height at a given time. Essentially, that's all that's referring to. H at t, or the height at a given time, is equal to negative 3 times t plus 1 to the power of 2 plus 5. So we have a quadratic, right? So we want to graph it and find the domain and range. It is going to take us back a little bit to grade 10, knowing the key components of this quadratic function and how we can graph it. So a couple things. The negative in the A value, the negative coefficient tells us it opens down. It is in vertex form. We remember what vertex form is. So the two values here tell us our vertex. In this case, it is -1 and 5. Remember, it's the opposite of what we see inside the bracket. So we know we have a point at -1 and 5. We know it's going to open down, something like that. Now, to be specific, though, we need to use our step pattern. Right? So the step pattern is 1A, 3A, 5A. Our A value in this case is -3. So that means our step pattern is 1 times -3 or -3, 3 times -3 or -9, 5 times -3 or -15. That tells us, again, we go over 1, down 3. That's our next point. Over 1, down 9. So we end up at -6. And the next one we can't really draw, but we can repeat it on the other side. Right? Again, our parabola is going to be symmetrical. So it would follow the same step pattern on the left side of our vertex as well as the right. And there we roughly have our function. So we want to we've graphed it, we want to find the domain and range. So the domain, again, refers to the x values. So it doesn't matter really any restrictions right now. We still set it up the same way. X is any real number. I can even do the range to start off. Y is any real number. Now let's look at any restrictions. Well, for the x values, the horizontal, right, it is going down. It does look very narrow, but it is spreading out ever so slightly. We can see with the step pattern that it will. So because the arrows mean it continues forever, there will be no restrictions on our domain or on our horizontal or our x values. So that means x can be any real number. For y, there is a restriction though, right? And that restriction is that it cannot be higher than 5. So that means that y has to be less than or equal to 5. Right? It can be anything else. It can be anything below 5, and the arrows indicate that. And we see that as well in the graph. Right? So the range is y is any real number given that it is less than or equal to 5. The second part says find h at -7, or basically find the height at the given time of -7. So find the height at -7. Now, if we had a graph, we could just go over to -7 and go down until we touch our function and find out whatever that value is, right? Whatever that horizontal value is, right? And that would be the answer. Unfortunately, with our graph, we don't see that. We can't see it on our graph, but what we could do, because we have the equation, we can use that. So h at -7 is equal to -3 times -7 plus 1 squared plus 5. We can go through and solve or calculate. -3 times -6 squared plus 5. -3 times 36 plus 5. We get -103. That means, therefore, when h is -7, or h at -7 is equal to -103, or you could say -3, -10, sorry, not -3, -7, -103. Another application, right, the temperature of the water at the surface of a lake is 22 degrees Celsius. As Chester scuba dives to the depths of the lake, he finds that the temperature decreases by 1.5 degrees for every 8 meters he descends. We want to model the water temperature at any depth using function notation. So a hint, it is a constant rate of change, therefore this will be a linear relation. So it will be y equals mx plus b. So we need an initial time and a rate of change. So going back to grade 9. Looking back, we see an initial temperature, right, at the surface of 22 degrees. We also see a rate of change decreases 1.5 degrees for every 8 meters he descends. So in this case then, we are going to use function notation, so we can say the temperature, or capital T, at a given depth, or a temperature at D, is going to equal, now we're going to have some sort of expression with D in it. Y equals mx plus b, negative 1.5 divided by 8, so that rate of change, times the depth, plus the initial 22 degrees Celsius. So that is our function for this scenario. Next part says, what is the water temperature at a depth of 40 meters? So in this case, we're being told depth is 40 meters, where D is equal to 40. So the temperature at 40 is equal to negative 1.5 divided by 8 times 40 plus 22. Again, we can go through and calculate this. 1.5 divided by 8 times 40. We get 15 over 2, or negative 7.5, or sorry, not negative. We get negative, plus 22. We get 14.5 degrees Celsius. Again, this is just a calculation, so as long as you're comfortable using your calculator, you should be able to solve that. The last part asks, at the bottom of the lake, the water temperature is 5.5 degrees. How deep is the lake? So in this case, this section here, this tells us the temperature at a given depth is equal to 5.5. Basically, it's telling us the y value, or you would have previously known it as, we're told the y value, now we need to solve for x. So we have our equation. We know that whatever this is, it has to equal 5.5. So 5.5 is equal to negative 1.5 divided by 8d plus 22. So I move the 22 over, so I minus 22 from both sides. I get negative 16.5 is equal to negative 1.5 divided by 8d. Then multiply both sides by 8. Get 132 is equal to negative 1.5d, negative. Then divide both sides by negative 1.5. And we get 88 equals d. So therefore, it is 88 meters deep. So again, the only thing new should be just how it appears, right? These questions are no different from things you might have seen in grade 9, where we had y equals mx plus b. You were given the x value and you had to solve for y, or you were given the y value and you had to solve for x. Same idea, it's just a different notation that we're going to be using with functions, called function notation. So essentially, just be aware of what it means, right? How it looks. If we had to plug things in, kind of similar if we scroll all the way back to these questions, right? What does f at 2 mean? What does f at negative 5 mean, right? The idea that it's telling us to plug a value in for x and determine where the function is. We didn't really see it in this example, but if you're given a graph, just go over to that x value and find out what that y value is. Couldn't really do it with this one because it wouldn't be visible on the graph, but if it was, you can just find the value on the graph at a specific x value. But again, that's what we've looked at today. Right? So again, new concept, new way of looking at old concepts, I would say.